Mhm.
Okay. Good morning, everyone. Sorry for the delay. We had some technical issues. Today, I'm privileged to introduce Professor Dale Purves. Professor Purves did his undergrad degree at Yale and then his MD from Harvard. And after doing a faculty position at the University of Washington, he moved to the Duke University as the founding chair of the Department of Neurobiology, where he is currently the George B. Geller Professor of Neurobiology and also a research professor. Previously, he has served as the director of the Duke Center for Cognitive Neuroscience and the director of the Neuroscience and Behavioral Disorders program at the Duke NUS Graduate Medical School in Singapore. He is a member of the National Academy of Sciences, the National Academy of Medicine, and a fellow of the American Academy of Arts and Sciences. And he has authored 18 textbooks on neuroscience. For the past 2 decades, his research has been on cognitive neuroscience and developing theories on explaining how vision works. And with that being said, I leave the stage to Professor Purves.
Okay, thank you very much. I'm really delighted to be here. I apologize for the delay in getting started. I hope you all have borne with us during that few minutes we were struggling. So as you can see from the title, I'm talking about how vision operates in a hidden world. And I'm very glad to be talking to some computer scientists because frankly, the future of understanding the brain and understanding vision depends not on neurobiology, but on people in computer science. And that's the direction that I think will solve some of the problems I'm going to talk about. So let me begin by asking a very basic question, and it is this. How does the visual brain work? And the answer is that nobody knows. And that may seem surprising after the last 70, 80 years of an enormous body of work on vision with all kinds of details at the cellular, molecular, and systems level. Why is it that we don't really know how vision works? Why can't we make a clear statement about the operation of this fundamental part of our nervous systems? And it's because the brain doesn't measure, has no access to physical reality. So what do I mean by that? So let's look at this very simple. I hope you can see my cursor.
Yeah, we do.
Yeah, okay. Let's look at this very simple example, which is probably one that you have seen before in some class or book that you've read. And it's a very simple demonstration of the fact that the luminance, the physical metric of light, is not what we see. And the example that demonstrates that here is if you look in the centers to simple stimuli, the centers are exactly the same luminance. If you measure them with a photometer, this one and this one are identical. But when one is placed in a dark surround and one is placed in a light surround, they look different. This one looks lighter. Lighter is the psychophysical name that we give to the appearance of luminance, and this one looks darker. Here, without these backgrounds, the two luminance values look the same. So what's going on here? Why is it that we don't see physical reality? And a demonstration like this should make you think about that. And the first thing that might occur to you is that, well, this is not a very dramatic example of the influence of the surround on the appearance of luminance, lightness, or darkness. Let's look at something that's a little bit more dramatic. So here is a better example of this. So if you look at these two areas, this area here, this area here, my slides are giving me a hard time. Okay, let's see if we can stick. So if you look at this area and this area, they look very differently light. This looks dark, this looks light. But if we take away the information in the scene, they look identical. They are identical. These two patches are physically the same, but when we add context to the scene, information from our past experience into what these should look like, they look very different. This looks very dark. This looks quite light. And that's a much more dramatic example than this. So my point here is that if you add more context to the scene, you can make these examples of lightness and darkness disconnected from their physical luminance look very different. Now, the next question you might ask is, well, is this in more complex situations? So let's look at this one. And here, this patch looks dark, this patch looks light. And this difference in the appearance is now coming from the context that's being supplied by this edge here, this gradient going from gray to black and from going from gray to white. And if you cover that up, suddenly these two patches look the same. If you take it away, you see the dark side, the darkness returns and the lightness returns to the superior and inferior patches here. Take it away, and instantly the perception that you have of light and dark changes. So there's something very unusual going on here that is basically making the point that what we see, our perception, is fundamentally different than what the physical world, in this case, these examples in the slides, are presenting to us. So is this something that's just relevant to lightness and darkness, or is this strange difference in phenomenology, does it apply to other perceptions? And our basic perceptions in vision are of form, color, motion. We've been talking about lightness and darkness. That's obviously the most basic aspect of visual perception, but we respond to stimuli that convey form, color, motion. These are the basic perceptual characteristics that vision supplies. So the question we're asking now is, does this odd phenomenology of not seeing what's really there in the world, does it apply to these other aspects, these other components of visual perception? So let's look at a simple one, which I'm going to come back to and show you more about later. But let's look at something that's been studied for, more than 100 years now. This was first studied in the 19th century, but here is an example of perception, our perception of form in the simple instance of length as a function of the orientation of a line. So here's a stimulus or a series of stimuli that show a horizontal line, a vertical line, and lines at intermediate orientations. So what people asked beginning in the 19th century and confirmed several times in the 20th is, what's the length that we see as a function of the orientation? do we see the vertical line and the horizontal line looking the same length, or are they different? And here's a result of that psychophysical experiment. And what's shown here on the x-axis is the orientation of the image. And what's shown here on the right is the perception of line length, how much longer we see the vertical line than the horizontal line. And the difference is pretty striking. It's about 10% difference. So here's the vertical line, and here's the horizontal line, horizontal, vertical, and you can actually see this. This again is something you've probably seen in textbooks or something you've been exposed to before. So the strange thing about this is, and I want to come back to this and show you how it's explained. Strange thing about this is this McDonald arches kind of psychophysical response. So it's not just that the vertical line here is 10% longer. You can actually see this here, that this line, it looks longer even than this one, even though they're exactly the same physical length. But this McDonald arches phenomenon is peculiar. The maximum perception of line length is not at vertical, it's about 20%, 20 degrees rather, off of vertical. So I want you to remember this. Again, the main point here is that for the moment, this doesn't apply, just this inability to see the world in its physical reality doesn't just apply to the lightness and darkness that we see, but it applies to other perceptual components of vision. In this case, the form, the length of the line in this very simple case. And I want you to remember this because we're going to come back and try and explain these phenomena in a way that I think will appeal to those of you who are struggling in computer science to think how the brain and the visual system in particular might work. So the question that people ask in response to these demos is, well, aren't these just illusions? In what sense are these really important? Are they just little tricky phenomena that have no particular relevance to the way we see the world? And the answer is, no, that's not the case at all. This is the way we see the world all the time. And to dismiss these as illusions would be a bad mistake, because the way we see the world all the time is telling us something very fundamental. The fundamental thing it's telling us is that we just don't see the physical world for what it is, measured with instruments. Don't have to be complicated instruments, rulers, protractors, photometers. They measure the physical world, but we don't see that physical world. There's a discrepancy between what we perceive and what we measure with the simple or not so simple instruments of physics. So what's the basic problem here? What's the reason for these discrepancies? And the answer is, if you think about it, really quite a simple one. And it's that the biological sensors that we have in our visual system, and this applies to basically all sensory systems, can't measure the physical world. So if you think about images projected onto the retina, you recognize that those images are not conveyances of physical reality, whether it has to do with lightness, color, brightness, form, motion. We just don't have that wherewithal to measure the physical reality that's out there in the world. The image is what we use as stimuli to somehow operate in the real world, but we're not taking measurements by virtue of the visual system's operation of the physical world as it is. So why is that? Well, the answer is really pretty simple. So if you think of a driverless car, for example, this happens to be a Tesla, much in the news these days. The Tesla operates, or any driverless car operates, by making physical measurements with digital cameras and other devices like lasers and rangefinders, a bunch of physical measurements that are mounted on the car that tell the computer system in the car what the physical world and its immediate environment is really like. But we don't have those measuring devices in our visual system, and we are basically stuck not being able to measure the physical world simply because we don't have the apparatus to do that. So what's the answer? I mean, if we don't have the wherewithal to do that, how are we getting around it? This diagram, incidentally, shows you just the problem that we are facing in the case of brightness. So here's the eyeball out here and the stimulus reaching the eyeball. And that stimulus is made up of illumination, reflectance from the surfaces of objects in the environment, the transmittance of the atmosphere that we're operating in at whatever moment it happens to be. And all of that information, the illumination, the reflectance, the transmittance, are all conflated in the visual image, in the stimulus. And we can't work back from the stimulus to disentangle the contribution of the illumination, the reflectance, the transmittance to the perception that we are witnessing. It's just impossible to do that. So this is the underlying problem. And what's the answer to that? Well, the question is, how can we behave in the world successfully if we can't measure it? And the answer is, well, nobody knows, but there is a strategy, an empirical strategy that could address this confound without making measurements in the real world. And what I'm going to tell you in the rest of the talk is using these examples of lightness and brightness and the example of line length, how it is that empirically we can get around the problem of not being able to measure the world with our visual system and yet gather information that would allow us to behave without measurement of the physical world successfully. So that seems a tall order, and the question is, how could that work? So let's go back to this simple example, and let me remind you that these two patches are the same luminance measured physically, but they appear different when there's a dark surround and a light surround. And the question that needs to be addressed here is, empirically, could information accumulated by trial and error as we've evolved in the world or as we individually live through our time in the world, is it possible that the accumulated trial and error experience can explain this kind of phenomenon and basically give the indication of how it is that in the absence of physical measurement devices, the visual system can gather information that allows us to behave successfully without making physical measurements of the world. So let me take you through how this operates. And again, it's pretty simple. And step one is, first of all, you have to collect information from the physical world to ask, what is the frequency of occurrence of lightness and darkness in the pixels, so to speak, that form the retinal images that we respond to. And you can test that by taking thousands of images like this of the natural world, again, under the, well, not again, but under the assumption that the physical world hasn't changed from day one for human beings, and ask, is the arrangement of information, is the patterns of light and dark that we see in the world, does that convey information that we can use to explain this phenomenology of the light and dark patches that I've just been talking about as an indicator of how it is that empirical experience can guide us to perceive things usefully, and I emphasize the word usefully, without knowing or making physical measurements of their actual characteristics in reality. So step one is, okay, gather a whole lot of information about the physical world by using a database of natural images of dark and light. And step two is then taking those pictures and millions of times, literally millions of times, apply templates that are like the templates we've been talking about. Sorry. The same luminance in a light surround and a dark surround. So here the question we're asking is, if we apply that template and monitor all the dark surrounds and ask what's the luminance typically in the center of that dark surround compared to the luminance of a light surround, and what's the luminance in the center of a light surround, you get different probability distributions. And just as you would expect from your knowledge of how the physical world is constructed, that things that are physically near each other tend to be made out of similar stuff. So if you literally do this millions of times and ask what's the luminance typically in the center of a dark surround versus the center of a light surround, you get, as you would expect, two different probability distributions. So the probability of the center of the dark surround, again, just by the structure of the world we live in, is going to tend to be dark, and the probability distribution here of light intensity against its frequency of occurrence is different from the same information gathered for the light surround. So again, we ask, in a light surround, what's typically the center of the luminance in the center? It's different, and you get a probability distribution that's a light intensity that is greater. So, and this is very simple. It's just what you would expect empirically. The frequency of occurrence of the center of this patch in a dark surround is different statistically from the center of the patch in a light surround. And here is the probability distribution shown in that way. And if you look at a cumulative probability distribution, the ranking of luminance in the dark surround versus the ranking of luminance in the light surround, you see that they are basically different. So here in the light surround, in the dark surround, the empirical rank is going to be much higher than the center, the statistical point, the empirical rank of the center of the information you gather in a light surround. And this difference is the frequency of occurrence of the lightness and darkness patterns that we've always seen, not for any tricky reason, but just because that's the structure of the physical world we live in. So the explanation of the difference that we see in this, the difference of the light surround or the same surround in a dark, the luminance that we see in the center of a dark surround versus a light surround looks different. And the reason it looks different is that's the experience we've always had. And the idea is that the frequency of occurrence of accumulated experience in the world allows us to see these differences, not because they're useful, but because they're an indicator of how it is that we have the problem of not being able to measure the physical world. We get around it by accumulating the frequency of occurrence of what stimuli have been, and in that way get around the driverless car problem of our problem, not having the wherewithal, the measuring instruments that exist in the driverless car. So let me go on to this example. And I said we come back to this and talk about line length. And remember, the issue here is that when we are presented with lines of identical length, we see vertical lines as 10% or so longer than horizontal lines. And we see the maximum difference in length, the maximum exaggeration of length for lines that are actually oblique. So what's going on here? Again, if you want to ask how it is we could get useful behavioral information empirically, you need to measure the frequency of occurrence of line lengths in the physical world and ask, does that gathering of information, does that frequency of occurrence of stuff in the physical world correspond, explain the difference that we see in our perception of lines of equal length, vertical being horizontal, longer than horizontal, and oblique being somewhat longer than either vertical or horizontal. So how do we do that? Well, in the case of lightness and brightness, it was simple. We just used a bunch of images of the real world in black and white and gathered the information from that database. Here, the database, the idea is the same. You need a database, and the database here is gathered in a somewhat more complex way by using a laser rangefinder to actually measure the frequency of occurrence of stuff in the physical world. That's lines that are vertical, horizontal, oblique, and the laser rangefinder, again, you're probably familiar with the operation of such devices. They send out a beam that uses the time between the emission of the light beam and its return to the sensor that tells you exactly at millimeter precision what the distance of physical objects is in the world that confront the laser rangefinder, which stands for you, the observer. So this is just the information that you get. The color coding here indicates the distance from the observer of objects in the environment. And to get the information about the orientation of lines, the frequency of occurrence of lines that we see, again, it's not hard. You take many, many images gathered by the laser rangefinder. You overlay those images with lines of different lengths and orientations, and you find out, not surprisingly, of course, that there is statistical variation in that. You get an indication of the frequency of lines of whatever length you choose to examine that are horizontal, that are vertical, that are oblique. And by, again, doing this millions of times, you get a statistical empirical result that tells you how often are the lines projected onto our retina coming from objects that are vertical, horizontal, oblique, and the result of that is what you see here. So here's our stimulus that we talked about before, vertical, horizontal, oblique lines. You use this to ask how frequent are lines of different orientations coming from the environment to you, the observer. How frequent are they in typical scenes? And the answer is that, remember, this is our perception. We see vertical lines, 90 degrees, as about 10% longer than horizontal lines at 0 or 180 degrees. And remember that the peaks, which are odd embellishments on this otherwise pretty simple curve, the peaks are a little bit off vertical. We see the longest lines perceptually, we see lines of the same length being longer perceptually when they're a little bit off vertical. So here are the perceptions predicted from the data of the frequency of occurrence of lines at these different orientations, taken from this information gleaned from the laser rangefinder findings. There's a very good match between this and this. So here, the frequency of occurrence of lines at different orientations coming from the real world, and here our perceptual response, and these two match fairly well, just as in the case of lightness and brightness. The match of what we perceive agrees with what we expect from the frequency of occurrence of information gathered over evolutionary and individual time. That is not just a few images, but a mass of experience that we have from day one as human beings seen. So this is, I think, pretty impressive. And again, I don't have time to examples in color and motion, other visual qualities that make the same point. But these are the simplest ones, and I think the easiest ones to kind of wrap your head around. And the upshot of this is that indeed, there seems to be a very good correlation between the frequency of occurrence of what we've seen in our experiences as individuals and our species over millions of years, and the perceptions that that empirical information generates. So what does that mean? What's the mechanism? How could we think about this in terms of brain function or computer simulations of brain function? And again, the answer is pretty, I think, intriguing. So I think today most people think about the brain realistically as a neural network. I mean, you know about connectomics and the almost infinite detail that actually exists in human and other brains, but you can basically take that and use the neural network as a kind of a description of that enormous complexity in terms of hidden layers that are feed forward and feedback, that have an input and an output. And the experience that we've been talking about, that we see in experiment from analyses of images in black and white, or analyses of images in terms of form using line length, and many other examples that we don't have time to go into, all of that can be thought of as encoded in a network of the species, or us as individuals, that has been placed there by millions and millions of trials to answer the question, or to address the question of how it is that we can behave in the world successfully without measuring things as the driverless car does with a laser rangefinder or a digital camera or any other physical measuring device that is now being used successfully in many, many applications. So what does that mean? So if we come back to biology, I mean, this is obviously an appealing sort of summary of how one thinks about the enormous complexity of the brain in terms of something we can wrap our heads around. Yes, it's a neural network of enormous complexity, but how can we think of that in terms of a biological way of addressing the reality of the nervous system? And the last slide I want to show you, or nearly the last slide I want to show you, is the example that I think makes pretty clear what's going on in the brain. So you're all familiar with the knee-jerk response, and this is a simple reflex that was first described in the early 20th century by Charles Sherrington and others. And it's an example, and I think a very good example, of how the brain is operating to generate useful behavior in response to empirical information. So this is an analogy, if you like, to the way in which useful visual information is generated by accumulated experience with images. This is information that's been generated in reflex responses to the sensory motor operation of the human being in a natural setting. So the reflex for a knee jerk, let me go through this. It's pretty simple, but there are stretch receptors in the muscles that extend the leg, and that sensory information goes to the spinal cord. It connects with motor neurons that go back to muscles that are both extensors and flexors of the leg. And the result of this reflex loop, again, coming from the experience over evolutionary time that the neuromuscular system has evolved to give us this very useful response, which prevents us from falling on our face when we trip. So you're walking along, you stub your toe, this reflex is thrown into action, the leg extends, and that prevents you, or helps prevent you, from falling down. And the reason I show this is that it's a simple biological example of how reflexes work. And the question that's, I think, raised by the stuff that I've told you about here in vision is, could this be an exemplar of really how all of the visual system and the rest of the brain are working in terms of using reflexes as a universal strategy for helping us get through the world, deal with the world that we can't measure in any direct way. So again, the reason for thinking that is the reality of these very detailed knowledge of reflexes in the sensory motor system. And if you think of the parallel in the visual system, what you're provoked to think about is, could the visual system be responsive to stimuli in the same very simple way that the knee-jerk response is elicited by stimuli, by having the connections that are needed to respond to the stimulus already there when the stimulus comes along. So it's obvious in the case of the knee jerk that the evolution of this protective reflex evolved over millions of years. The connections that are shown here, they're ready to go. They just need to be triggered by stubbing the toe. And when you stub your toe, the reflex is triggered and you have a useful response. You tend to be protected from falling down. So is the same idea practiced in vision and indeed all the rest of the brain, that the connectivity in the neural network, that's the brain, is that information, is that connectivity already there when the stimulus comes in? And the argument that I think follows from what I've told you today is that in the case of lightness, brightness, and in the case of form, using the example of line length in relation to the perception that we have elicited of that, do those things arise from the fact that that connectivity is already present and just needs to be triggered? There's no computation. There's just a triggering of reflexes, connectivity that's been put in there over millions of years to prepare for the circumstance that we encounter all the time in the case of a sensory motor reflex like this, or in the case, arguably, of reflexes that are involved in the same way in vision. Again, the point being that if the connectivity is already there, it just needs to be triggered, you have a very effective way of dealing with a world that we can't apprehend directly, but can be used to generate useful behavior based on the accumulation of experience over millions of years or tens of years of our individual existences on the planet. So let me summarize that, and then we can open this to some questions if you like. What are the key points that I have made here? Well, I think these should be pretty obvious, but let me summarize them nonetheless. The fundamental challenge in vision is that real-world sources of images can't be known directly. We don't have the physical measuring apparatus to know what's out there in the world in any direct way, in the sense that a driverless car can measure that information with physical instrumentation. The apparent solution to our position as animals that don't have that information is to generate percepts entirely on the basis of accumulated trial and error. Again, one can think about that usefully in the reflex response of the knee jerk that protects us from falling. Extend that to vision, and you can see the utility of the same general idea. The evidence in vision is that what we see in the basic domains of visual perception, form, lightness, brightness, color, motion. Again, I haven't had a chance to go into all of these, but I've shown you some. That is pretty impressive evidence that, yeah, the brain really could work in this way, that the percepts that you see are determined when you do the experiments by the frequency of occurrence, or at least they fit with the frequency of occurrence of stimulus information gleaned over long periods of time. And finally, the point that I would end with is that if this interpretation is correct, then visual circuitry and what it's trying to do will need to be understood in this general way, and you can extend that to the brain. And again, ask, is this something that is, for computer scientists, a way to think about the way forward in understanding the brain that, frankly, has not been adequately solved by neurobiologists who've done wonderful work in studying all the aspects of the brain from, again, as I said, a systems study or molecular anatomical point of view. But none of that, including the classical work that we think of as being the basis for current thinking about vision, none of that really can answer the problems that we've been talking about in this last 45 minutes or so. So if you want to read about this, there are a bunch of books that are out there that you can look at, and the books have, of course, references to lots and lots of papers that are relevant, but there's no lack of information about what I've told you if you want to read more about it and think along these lines about whether that's really a useful or indeed inevitable way of thinking about how the visual brain works. So let me end there and open it to questions. And again, I appreciate your patience while we had a slow beginning with technical difficulties. Thank you.
Thank you so much for this interesting talk. I always find this comparison and your perspective about the way that brain works very interesting. So any question from the audience, you can type in the Q&A box and I can ask on your behalf. While you're thinking about your question, I have a question. So I think one of the major differences in your view about the way that a brain is working is to make the distinction between the way that we usually formulate understanding in terms of logic and symbols, abstract concepts, thinking about doing computation, and then also, in your view, evolution through the notion of usefulness, which might be describable with mathematical operations, but that's not the way that the brain works. And in terms of computer science, I think we can see that distinction between symbolic logic and reasoning on one hand, which used to be kind of the dominant approach for AI before deep learning, and deep learning itself, which might be a little more similar to your thinking. Now, my question is, from the works on deep learning that you've seen, what is the shortcoming you feel that it is still there? And we've seen that when we moved from symbolic logic to deep learning, we made a significant improvement in the way or in the performance of AI. What shortcoming do you think that we can overcome, and still deep learning is not exactly similar to what the way that brain is working?
Yeah, that's a very good question, one that I spent a lot of time thinking about. So let's first of all define deep learning. And deep learning is, as you suggest, basically algorithmic. So as Terry Sinowski puts it, deep learning is following a series of instructions, much as you would follow a recipe in baking a cake. And the difference in the advances in deep learning, which are amazing. I mean, this is really a wonderful advance in the technology that, has many uses and examples that you know about very well. The difference is that deep learning is based on using data to inform a procedure of algorithmic classification. So you want to tell, I mean, I'm being very simplistic here, but you want to tell dogs from cats, you present a deep learning system with thousands of images of dogs and cats. By using back propagation, you feed them success and failure, and pretty soon you have a system that is very, very effective in telling dogs from cats. And you can extend this simple description to many applications of deep learning that are terribly impressive. But what it's not doing is what I talked about this afternoon. So it's using the data to classify different categories of things in the world, objects in the world. And that's very, very useful, whether it's for, baggage screening at TSA or recognizing faces of potential criminals, or what all of the many things that deep learning has proved useful in doing. But it's algorithmic, it's using classification, and it's not taking this step that I've talked about this afternoon, which is, I think, the essential step in moving from classification to another way of thinking about learning, which is not classification, but just using the empirical frequency of information in image of vision to explain how it is that we can see lightness, darkness, color, form, motion in the way that we do, by asking in a very simple way, does the accumulated experience that we measure with databases, excuse me, in this way, does that conform with the way we see in the cases that I talked about this afternoon, lightness and darkness, or line lengths? So there's a ways to go, in my opinion, from where we are now with deep learning to the next step, which is going beyond deep learning to, in an empirical, totally empirical way, ask whether a computer can solve problems that exceed the challenge of classifying dogs and cats and the like.
Mhm. Thank you.
Let-
Yeah.
Let me make one more point there. I mean, so I think if you're familiar with the work of the people at Google DeepMind, and I'm talking about the Dennis Hassabis and Silver group that's worked on
Yeah.
game playing, whether it's Go or chess or what have you, that they're going in the right direction. They're using a completely empirical challenge to make a computer that can beat all comers at complex games, and there are good reasons for why that might have to be done when the problem that needs to be solved is far more complicated than dogs and cats.
Thanks. Okay, it seems that we don't have much question from the audience. Thank you again for your talk, and I'll follow up with you maybe to discuss later.
Okay, thank you.
Thank you. Have a great rest of your evening.
You too.
Bye.